Good evening, and thank you for joining us for this live streamed astronomy presentation, Searching for Life on Mars with the Perseverance Rover, with Nina Lanza and Roger Wiens. I'm Rick Wallace with Pajarito Environmental Education Center, or PEEC, located in Los Alamos, New Mexico, and I'll be the moderator for today's talk. We are able to offer programming at this time because of our wonderful members and donors, so we'd like to thank you for your continuing support. Okay, let me first mention our first presenter. Roger Wiens has led instruments on 3 NASA missions, Genesis, Curiosity, and now Perseverance. For his PhD, he analyzed samples of Mars that came to Earth as meteorites. He was awarded an honorary doctorate in France and was knighted by the French government for forging strong ties between the French and American scientific communities and inspiring many young, ambitious Earthlings. His book, Red Rover, was at least available at the Bradbury Science Museum. Asteroid 41795, Wiens, is named after him. Let me also introduce Nina. Nina Lanza is on the science teams for the Curiosity and Perseverance rovers. Her current research focuses on understanding the origin and nature of manganese minerals on Mars and how they may serve as potential biosignatures. Nina was a field team member for the Antarctic Search for Meteorites project during 2015 and 16 season, for which she recovered meteorites from remote field locations in Antarctica. She probably thinks Los Alamos is warm. She is also a regular contributor on the television series How the Universe Works, which is on the Science Channel.
We are so excited that we're just 14 weeks away from the landing of NASA's next rover. So the title of this talk is Searching for Signs of Life on Mars with Los Alamos instruments on the Perseverance rover. And we've had such a fantastic time exploring Mars in the last decade. And I am still wearing the landing shirt, this blue landing shirt from the Curiosity rover landing. And I'm also wearing a mask that you can see right here, which has the Curiosity, in fact, the ChemCam instrument right on it. Most appropriate, and all of our team members that operate ChemCam here wear that. Thanks to Cindy Little, who actually made those. So we have been exploring Mars for the last 8 years with Curiosity, but we didn't start there. The real Mars era of exploration with rovers started in 1997. I was around back then, and it was such an internet phenomenon at that time, just in the nascent internet era. But this was only a 22-pound rover, and it only lasted for about 87 days. But it truly told us that we could do great things on Mars, even with a little rover. It was followed up in 2004 by twin rovers, Spirit and Opportunity, and one of them lasted all the way to 2018. So these were pretty exciting rovers, but they were pretty small still. And if you can imagine, although they were about the size of a golf cart, they had only a few pounds of payload instruments, scientific instruments on them. And so we really longed for a day when we could get like a mobile laboratory on Mars. And we got our wish with the Curiosity rover. And so there it is. And it was a 1-ton, it is a 1-ton rover with a 450-pound arm on it. And it could drill samples to let samples into some of its instruments that sit inside the rover. And this was Los Alamos's big moment with getting involved with Mars exploration on the surface of Mars. It was our first instruments to go to the surface of Mars with the ChemCam instrument. And then Los Alamos also supplied the power for this rover as well. And Curiosity is still going. It is not finished at all yet. And so here's a picture of the great terrain we have in Gale Crater. And we've made this a part of this traverse. In 2018, we were going all over this big ridge that we were exploring. And then in 2019, we dropped down into an area called the Clay Bearing Unit. This year, we climbed all the way up onto a pediment, this I don't know if you can see it real well, but it stretches all the way up into this canyon, this long pediment right here. We started to understand more about that. And now we've dropped back down. We were skirting along here and then decided to go down here for one more analysis of the clay material with the SAM instrument that studies organic materials. And then we're going to be going, in fact, just this weekend, the rover is heading off after about a month and a half in one place. And in fact, Nina and I are on the operations team on Monday when we'll be driving away and getting going. So we're really excited about that. And we'll head up to the sulfate unit. And then we'll go up through a narrow canyon here and onto the pediment again, and then up into Geddes Vallis. And so this mission still has some really exciting terrain left in it. And Nina, why don't you take it away and tell about some of what Curiosity has found?
Sure, yeah. I mean, so in the time that we've been on Mars, we have learned so much. And as Roger said, we're going to learn so much more. It's really exciting. So the major finding of our mission is that there was once a lake in Gale Crater, or a series of lakes. So I'm showing an image here. This is a computer-generated image, but it's using real topography data from Mars. And this is an artist's conception of what that lake might have looked like. And so this means there was a long-lasting body of water on Mars. And so this is, of course, a place that on Earth would have been inhabited, but of course we don't know if it was inhabited on Mars, but it was still a really habitable place. And conditions were very habitable within that lake. So we know that the fluids were conducive to life, so they're kind of neutral. And we've also found a lot of these water-formed minerals that all point to a very habitable environment in this lake, something that we'd recognize if we saw it on Earth. And excitingly, all the building blocks of life were present. So not just the life-forming elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, like I like to call that chinops, but there are many others. We've actually found, excitingly, traces of organic carbon. And so this is carbon that is available for life to use. And we found this within organic molecules. And so these have all been preserved in the sediments. So that is really exciting because, again, that tells you that everything that life ever needed would have been present there on Mars in Gale Crater, in this lake or series of lakes. But it's not all just exciting in the past. It turns out that in the present day atmosphere, we're actually seeing traces of some organics today in the form of methane. And so methane is a gas that we might know, from volcanoes or life on Earth, but on Mars, we don't really expect it. And one of the exciting things about it is that if we detect it now, that means it's being produced somewhere today on Mars. It doesn't last a long time in an atmosphere. So it only lasts maybe 100 years. So this methane is being produced today. And we get little whiffs of it. And we keep sniffing the air and keep getting little whiffs of methane. And we're not totally sure what is producing it or where it's coming from. But it's a really exciting finding because at the very least, it tells us that Mars is still an active place. Things are still happening on the surface and the near subsurface. And so, I think there are a lot of surprises still waiting for us. So again, this is an ongoing mission. We're not stopping at all. There are a lot of discoveries that are yet to come. So do stay tuned for our discoveries. Thanks.
Yeah, and it's kind of like I hate to move on to the Perseverance rover, but we are, and we're doing both, and that's the truth. So here you have the two rovers. They are almost twins in a sense. I think Perseverance on the right is about 6 centimeters longer than Curiosity on the left, but they are actually very different in their mission and in the instruments that they have. And so we will be pointing that out throughout this talk. Also, Perseverance is a little heavier. It's got a little more equipment on it. And so we'll just be unpacking that for you. So Curiosity's goals were to assess Mars' biological potential, and you just heard about that, and characterize the geology of the landing region. Again, it was a lake and it was habitable, and also to characterize human hazards, and that's ongoing. So by comparison, here is Perseverance's goals. And so it will explore the geology of the landing region, look for habitability again, and seek signs of ancient life. But it's got two other goals that are very different actually down here. One is to gather samples that could be returned to Earth by a future mission. And then also to demonstrate a technology for future robotic and human exploration. So these are very interesting sort of forward-looking goals that we'll be talking about during this mission. And here is the Perseverance rover with some labels for all of its different instruments. And there's several different categories. So this is remote sensing. It's the instruments that look from some distance away. And we have the Mastcam Z. It's a zoom stereo camera. And so it has something like Mastcam on Curiosity, but it actually has a zoom lens feature. And then we have SuperCam, which we built here, and we're going to talk about later. Then in terms of the ARM instruments, or what we call the proximity instruments, there are two instruments. One is Pixel, which is an elemental chemistry instrument that gives us very fine scale chemistry within a fraction of an inch. And then its companion is Sherlock. And I'll be talking more about Sherlock because part of Sherlock was built here at Los Alamos as well. And then in the environmental category, we have two instruments, RIMFAX, which we'll tell you a little bit more about later, and META, which is we'll just be covering right now as a weather station. It has several different features for the weather, the temperature, the humidity, and also the ultraviolet and various things that are important on Mars in the dust loading of the atmosphere. And that is actually a Spanish contribution for this mission. And then we have some really exciting things that I just mentioned. One is Moxie, which is the demo for the sort of feed forward to humans. And then this tech demo, the helicopter that you all want to hear about. And so, Nina, why don't you talk about the helicopter?
This helicopter is so cool. Okay, so just to keep in mind, we've never sent a helicopter to another planet. So this is the very first one. And it's actually a really huge engineering challenge because Mars has a much less dense atmosphere than the Earth. So you have a lot less air to push with your rotors. So we actually need really big rotors to be able to do that. So Ingenuity is going to be our test of whether we can do this. But with that, the reason we're going to do this is not just to say, oh, fun, we can fly a helicopter. It's actually to develop future missions to Mars and other planets. So the idea is that this helicopter could actually be a scout for our rover. You know, we have orbiting spacecraft that take images for us, but they're pretty far away. And it would be really helpful to have a little helicopter to just zip over, take a look at something, see if it's interesting. And then if it is, the rover can drive over there. And if it's not, then the rover can go somewhere else. So those are the science reasons why we'd want to do this. But of course, it's just really cool. So we're going to be testing that at the beginning of the mission. And so this is a solar powered helicopter. So we're going to do several test flights and we're going to have to let it charge up. So it's going to take a little time, but I think it's going to be absolutely so thrilling and exciting when we do it.
Oh, and
so go ahead.
Here's the picture of how it's going to Mars. It's actually, this is the underside of the rover. It's right on the bottom of the rover. You'll see a picture later where it's all covered up with a protective cover. But that's where it's going, and it's all folded up. It's just like, I hope it all unfolds okay. But we're excited here about this because we would love to use, as Nina said, this helicopter to have new ways to explore the red planet. One of them that I'm particularly excited about is you could use a helicopter to go into a cave on Mars. These caves tend to have vertical openings. And this cave that I'm showing here was a picture taken from orbit. And this cave opening is more than 1.5 football fields wide. And so that's big. And it's at least that deep. And it's a place where I would love to go and explore in the future. And in fact, after SuperCam was developed here, then a number of us got together and said, let's try to develop something that we could do next. And so we put our sort of our efforts into this thing called OrganiCam. And it basically takes camera images that will help light up in organic materials if there is some there. And so if we can make this kind of an instrument small enough and light enough to go on a small future helicopter, I would love to send this into a Mars cave. So we're always trying to think ahead, of course. But for now, I guess we have to go back to what's on Perseverance rover. So Nina?
So I have to say, going into those caves is going to be incredible because, if there's any place that's habitable on Mars today, those are it. So those are pretty exciting. So before we go into those caves, of course, we're going to go back to Mars with the Perseverance rover, which of course is en route right now. It's on its way. And so I'm just going to tell you a little bit about some of the instruments. So another technology demonstration that we're doing in addition to the helicopter is an instrument called MOXIE, which is the Mars Oxygen In Situ Resource Utilization Experiment. So MOXIE is a nice shorthand. And so what this instrument's going to be doing is it's going to be producing oxygen on the surface of Mars from the atmosphere. Now, that's something that we can do pretty well here on Earth, but the thing that's tricky here is that we've got to build an instrument that's robust enough to go into space, launch off this planet, and land on Mars, and then work really well. And so what the plan for this is that it will demonstrate that we can produce oxygen on Mars. And so this is going to be for future human missions to Mars. So not only for astronauts to breathe, because we need oxygen, but we also need to have some rocket fuel so that they can come home. And so oxygen is a really important component of rocket fuel. So that's the two things that we're trying to do with MOXIE. And I think that'll be a really good demonstration and a step forward for our human spaceflight. So another instrument that we're sending is called RIMFAX. That's the radar imager for Mars's subsurface experiment. So this is actually a radar instrument, as you might imagine. So it's imaging the subsurface materials. And the way it does this, essentially, it sends a ping of radar down and looks at the reflections that come back. And so we can actually see the structure of the subsurface, the near subsurface, without actually digging any trenches. And we can find things like a pocket of frozen water, perhaps, or even some liquid, briny water that might still be liquid today. So this will be really helpful for us to see into the surface and not just look at Mars on the very surface, but actually understand it three-dimensionally.
Now I'm going to tell you about the Sherlock instrument and its companion Watson. It turns out that Sherlock was proposed, and when the team from JPL was proposing it, they were looking around for who had experience with building certain parts of certain components for the instruments, and they said, Los Alamos does with the ChemCam instrument on Curiosity, and so they came to us, and we partnered with them on this, and Tony Nelson actually was leading the technical development of our part of Sherlock, which was the detector and the electronics for the spectrometer. So Sherlock is actually the instrument that will do the looking for organics with the Perseverance rover. So that's pretty cool. And it's mounted on the arm, and it has detection limits down to 1,000 ppm for some very, very tiny spaces, but then something like 10 parts per million for something that's a little bit broader in organics. And so we're hoping that we can find some organics with this instrument. Its inlet is right. It's just an imaging device, but it's looking out of right here. And then Watson came about because the engineers on the rover said, we need an instrument that will be able to look all over the rover and check its health. And by the way, it can do a lot of good science too. And so NASA decided to put a copy of the Molly instrument, which is a close-up hand lens imager on Curiosity, on here, and we named it Watson. And so that close-up imager is going to be great for science. They have two different places, so we'll have to move the arm a little bit to look at the same spot. That's not a problem. And so it'll be looking at very small spots to really understand and look for organic materials and some minerals as well. And so we're really excited to be a part of that. Now, just to give an example of what it would do, this is a picture that I took in the outback in Australia about a year ago. And these are some of the Earth's oldest fossils. And so we have basically sedimentary layers that would be one on top of another, but there was a microbial mat, some organic slime that was growing in these sediments, and it made this just fold up into a conical shape with all the stickiness of that mat. And these are the Earth's oldest evidence of life, basically. And so you'll find organic materials in these stromatolites. By the way, there are stromatolites that are growing today, but these are from 3.5 billion years ago, oldest things on Earth. And so that's the kind of thing we would be looking for on Mars, potentially. And so the Sherlock instrument took one of those, the team took one of those, and this is a visible image of some of those layers that you just saw. And this is their spectrum, and they get organic peaks here in their spectrometer, and then they get carbonate and silicates. And so they've made that into a map, a small map of just a few millimeters across, but they can show you the organics, which are colored green in this, the silicate, which is red, and the carbonate, which is blue. And so looking at the color map, you could figure out where the organic material was from the living organisms in this ancient fossil. And that's what we would be trying to do, will be trying to do with the Sherlock instrument on Mars. Nina?
So, I mean, that's so cool, right? We've got so many things, so many great science instruments, but we also, in addition to these science instruments, we have other instruments that help us do all of the rover's work. So there's actually 23 different cameras on this rover. I mean, that's amazing, right? We think, oh, you know, you snap a picture, it's just one camera. We've got cameras everywhere. There's one on our instrument, SuperCam. There's Watson, as Roger was just mentioning, but we also have cameras like the hazard cameras. So you can see there's some in the back just to help the rover navigate the terrain somewhat autonomously. So we've got some has cams there. We've got some has cams in the front. We've got some navigational cameras. So we actually are taking images all the time with this rover. We've got a lot of great ones. So there's going to be just an incredible treasure trove of beautiful images from this mission, and they'll all be publicly available. So you can take a look and see what are we looking at on Mars, you know, maybe not exactly the day of, but really soon. So you can see where we're sitting. So keep that in mind.
Now we're going to talk about our favorite camera, which is SuperCam. And so this is actually the cover of our proposal that we sent to NASA to try to convince them that they should fly this instrument. And it was sent in just a year and a half after ChemCam started working on the surface of Mars. And what we promised was that we would do the same thing as ChemCam, the chemistry, and that's with what we show as a red laser beam here, but it's really invisible infrared. But then we show a green laser as well, and that's to provide some mineralogy. And there's actually two techniques that will give us the mineralogy, and then we have imaging, and then not on this proposal cover is a microphone. And so we're going to tell you just a little bit about all of those things right now. But first of all, the chemistry is done just the same as ChemCam. And so here's a little video clip from ChemCam. And so first just showing that it's a point, focus, and shoot instrument. And then both ChemCam and SuperCam have parts of the instrument that sit inside the body of the rover down under. And that's the part that does a lot of the spectral sensing with these spectrometers here and these optical fibers. We get the light from a long fiber from the mast. So up on the mast, here is the laser right here. And then that laser fires out through a telescope that we're just opening up here. And this was a video done at Los Alamos back with ChemCam. And we're going to fire this laser at a nice big iron pyrite target about 6 or 7 feet away. And first we're focusing it, and then the laser is actually invisible, like I said. And so you'll just see the flashes, hopefully on your Zoom. There, I'm seeing them. And those flashes are produced by the laser beam hitting that target in a focused spot. And there you see it in a still sort of captured image. And so that's bright enough that we can do that 20 or 25, up to 30 feet away in some cases. And so we use that light. Actually, if we look at the color spectrum of that light coming back to that telescope and through the spectrometers that we have that we just showed you, it looks like this. And so the color of the rainbow that we see with our eyes is down here. The 3 spectrometers that we have, they go way into the ultraviolet, some into the violet, which is down here, and then the visible and near infrared, and then a little bit past what our eyes can see out here. But what we see are atomic emission lines from the different elements that we've just zapped with that laser and blown off of that rock. And so by the wavelength, we can tell what element it is, and we can calibrate that to tell what the composition is of any rock within 25 or 30 feet of that rover. And that's way cool. But so then to add to that, we wanted to add 2 techniques that would give us mineralogy. And so why do we need something else besides the chemistry? It's because the mineral structure can tell us more about the origin of the rocks. Remember, what we're looking for here is kind of to read the storybook of nature, the storybook of the geology, to understand what was happening when these rocks were formed. And so part of that is the chemistry, but part of that is the structure of those chemicals. So here is a compound, calcium carbonate. And this calcium carbonate would look the same to ChemCam, but it has two very different mineral structures. One is calcite. This is a really nice crystal of calcite. It's usually not clear, but it's all around on the earth. And then one is aragonite, and aragonite is made a lot by living organisms on the earth. So you can imagine that it's very important to see the difference in the structure between calcite and aragonite within this same chemistry. And so that's why we do mineralogy with SuperCam. And so this is just a collage or a mosaic showing the SuperCam instruments, laser firing here. We showed you this already. Now the green laser, and when we fire it, it looks like this. It's extremely bright, again, over 4 billionths of a second, and that's what gives us the mineralogy. So here's the spectrum that we get for the minerals. And so the minerals are labeled along here. The laser beam in this wavelength would be down here. Green is in the visible range where we could see it with our eyes. And then this is a shift in wavelength relative to that laser beam. You can see all these peaks, and these peaks all tell us about, if on my screen is hidden, but there are little molecules bouncing back and forth on the right-hand side that show you that those vibration frequencies are what give us these characteristic peaks of the minerals. So that's what we're going to be doing with SuperCam that we're not doing with ChemCam.
So there are, though, some things that are going to be really similar capabilities between ChemCam and SuperCam. And so one of those things that is just so cool that we didn't realize until we went to Mars and shot some rocks is that we can actually blow dust off of a target. So what we're looking at here is probably my favorite rock on Mars. His name is Steven. And so we've analyzed Steven many times, and Roger's pointing to some of those holes there. You can actually see that we've analyzed the material there. So we have chemistry, but you can see the dust all around it has been blown off. And on a farther away picture, you can see that we've shot several pieces, and you can see it's really shiny under that dust. And that's actually a really great capability because, we aren't going to be there to be able to dust off all the rocks. And it turns out that Mars is really dusty. So this allows us to remove the dust to see and observe the compositions beneath the dust. And that's not just useful for our instrument, but it's also useful for the other instruments that are going to be looking at those same targets. Yeah, so I think, so there's the laser pits right there. And then, I just want to emphasize here that the laser that we're using to get chemistry, the LIBS laser, is a really small scale laser. It's under 0.5 millimeter in diameter. And so we can actually get these really fine scale measurements. So what we're showing here is just an example of several things that we can do. So over on the left is a rock named Harrison. And Harrison has a lot of these white crystals embedded in a dark matrix. And so with the LIBS, we're actually able to see the difference between those two compositions. That's a really fine scale. If you look, the scale bar as a centimeter. So that's a really tiny set of chemistry measurements that we can do to be able to understand the geologic origin. You can also see in the middle image, there's another example of a rock that has dark material embedded in a light matrix. And we can see the compositional differences between those because we can analyze those two different materials. But one of the most cool things I think that ChemCam does and that SuperCam will do is that we can actually analyze in the subsurface just by analyzing in the drill hole that we make when we do a drill with the arm. So look at the scale. This is crazy. So the hole is about a US dime in diameter. This is a teeny tiny hole, and we are so far away from it. We're many, many feet away, about 10 feet, I think, when we actually do the analysis. And look, we're able to target. You can see that we have targeted a line with the laser, our little ablation pits there, down this hole. That's incredible. It actually, I'm not sure we thought we knew how to do it before we tried it, but now this is an incredible opportunity for us to sample in the subsurface. Even though we don't have any shovels and we're not breaking rocks open, we can actually get chemistry at a distance in the subsurface. So this is something that we'll be able to do not only continuing with ChemCam on Curiosity, but also with SuperCam and Perseverance. So now I want to tell you a little bit about another part of SuperCam that Roger mentioned. It's one of my favorite parts. So you can see here, this is SuperCam without its protective housing. And you can see in the red circle, that is the microphone. So we are sending a microphone to Mars. So why would we do that, right? That's kind of weird. And so I think the next slide has one option for why this is. Of course, so that we can listen to what the aliens have been saying about us this whole time. But in fact, no, we can really do some great science with this. So we can learn a lot of different things. So first, we can, of course, just listen to the ambient sounds on Mars. So that sounds of wind, moving materials. We can also listen to the sounds of the rover as we are doing other work. And so one thing actually that we're working on is a collaboration with MOXIE, the instrument that is doing the oxygen production. They've asked us to turn on our microphone when they are operating. So we can actually help them understand the health of their instrument with this microphone. But it turns out we can actually do a lot more. So the LIBS laser that we've been talking about that gives you the composition, it actually makes a kind of a zapping sound under an atmosphere. It's not really a pew pew, it's more of a snap snap, but it's audible when you have an atmosphere. And so it turns out if you listen to the sound that the laser makes as it's doing an analysis, you can actually learn something about the properties of the rock that it's analyzing. So you can learn things like how hard is the material. You can figure out how far we are ablating into the material. So we're digging a little hole every time we pulse the laser. And so how far did we go into the rock? And we can also identify whether or not there is a rock coating, which is really of interest to me, as this is something that I study. It just helps you understand the history of the rock's interaction with water and with the atmosphere. So actually, I think this microphone is a really exciting opportunity to test some new science. You know, geologists don't usually use acoustic data in this manner to be able to analyze rocks like this, but we actually have a great opportunity here to sort of to found a new field of geologic analyses. So I'm excited to do that. So so the next slides we're going to show you are just a little bit about our landing site and where we're going. So I'm showing here a topographic map of Mars. So the warmer colors are higher in elevation and the cooler colors are lower in elevation. So right away, you can see that there's a really big difference between the northern hemisphere of Mars and the southern hemisphere of Mars. The northern hemisphere is very low and smooth and doesn't have a lot of craters, whereas the southern hemisphere is higher in elevation and is very cratered. And this is already a clue to us as planetary scientists that some process has acted on Mars to resurface the northern hemisphere. So things are hitting, impactors from space are hitting Mars at the same rate everywhere, but only in the northern hemisphere have the traces of those impacts been erased. So we're looking at sort of a younger surface in the north and an older surface in the south. And so we thought we would choose for this rover a place that is kind of in the boundary place. So you can see I have a red box around here around the Perseverance landing site, which is a place called Jezero Crater. So it's actually a very small crater, and we'll zoom in on that a little bit. So here you go. So this crater is a fairly large crater. You can see the scale bar in the lower left. So it's tens of kilometers in diameter. And so you can see right away, there's some really interesting morphologies here. So there's labeled here is that there's an inlet valley and an outlet channel. And you don't have to be a geologist to think, hey, that kind of looks like a stream. And indeed, we think that is why what formed those features here. And the thing that really clinches it for us is in the landing site. If you can see that there's a white sort of oval near one of those inlets there. And so we're going to zoom in a little bit there. You can see there's a really interesting feature there that I'm going to tell you a little bit about. So one of the things that is just a dead giveaway for a lot of water over a long period of time is this delta deposit. So on Earth, a delta forms when you have a river or a stream flowing along, carrying sediment, and then it enters a larger body of water, and all those sediments are deposited, and it makes this fan shape. It's very distinctive, and you can see this on Earth today in modern systems that are still producing the delta. So what we're seeing here is an ancient delta on Mars. It's all the water has gone away, right? There's no lake there now, but the sediments remain. And so we know that this is a place that had a lot of water. And we can actually see in remote sensing data that there are minerals that are very suggestive of forming in water. So Roger's blinking back and forth there, and you can see we have something called a smectite, which is a type of clay. That's something you would absolutely expect to see in a delta and a lake environment. But we're also seeing a type of material called a carbonate. So this, you might know, a very famous carbonate rock on Earth would be something like a limestone. And so we're seeing this carbonate in this landing site. And that's really exciting because it's actually something we have sort of had tantalizing hints about, but have never really had a big observation in situ on Mars. And so this is an exciting place for us to actually maybe get some of that carbonate material and better understand how it formed. On Earth, carbonates form in these habitable places that have relatively neutral pH waters. And so this is something we want to know, if these carbonates are indeed there, that really tells us a lot about the environment that this delta was formed in, and specifically this lake. And sometimes people say, okay, well, Curiosity went to a lake. This is exactly the same thing, right? No, it's actually very different. Even though Gale Crater and Jezero Crater are around the same age, they are actually very different mineralogically and morphologically. So we can actually learn a lot by studying another lake area on the same geologic time on Mars. So Roger's going to tell you about what we're going to do with some of those samples.
Yeah, thanks, Nina. Now we're going to talk about one of the most important parts of this mission, besides SuperCam, of course. And that is that this mission is going to be getting samples that we hope to bring back to Earth. And we have never done this before, but Perseverance has a drill, so does Curiosity, but Perseverance's drill is a hollow drill, and it is made to collect drill cores. So I've got a little video here that shows what it's going to do with these drill cores. So this hollow drill is going in. Now it's got the drill core in the drill bit in a tube, and is bringing it to the rover. It meets the turret here. That turret will bring it down into the sample cache system, C-A-C-H-E, cache, which is to collect samples. And here's another arm, and this arm then takes it past an imaging station, a capping station, and then finally to a storage. It doesn't show the imaging and capping here, but it goes right to the storage here. And so you can see that there's a place for 38 tubes there. These are the sample tubes that we'll be using and bringing back from Mars. And so you can see on the left, this is what they look like. They're holding this little bit of sample core in them. Nice thing is we get something from the inside of a rock like this, and from the surface of the rock right on the top. And so this is what it'll look like. We'll have up to 38 of them. Then the rover is going to drop them on the ground somewhere, and waiting for a future mission. And so we can drop any of these at once. We can drop all of them in one place, but we're probably not going to do that. We're probably going to collect some, and then we'll drop them just to make sure that we got something on the ground, and maybe drive the rover to a more dangerous, risky place. But if the rover were to get lost there, we'd still have something there ready for the sample return. And then, but of course, if we're successful, which we expect to be, we'd bring them back and sort of make what they call a depot right here of samples. And we might make a couple of these, one in Jezero Crater and maybe one way outside of the crater somewhere else. So this is going to be a really interesting part of the mission to see where do we actually take the samples and where do we deposit them. And I'm sure there's going to be a huge amount of discussion. It's going to be a political issue, hopefully not too political. I hope Mars never gets political, but anyway. And then we have more parts that have to happen. So here is, well, on the left-hand side, we have Percy dropping the samples down here, and there's actually several of them all in one area right here. Then NASA's already working to develop the next mission. And this is going to be the big, difficult one because it has what we call a Mars Ascent Vehicle, a MAV. And that has to come down to the surface of Mars along with a little fetch rover. And that's because Percy wasn't designed to actually load these samples onto this next rover. we don't even know if Percy would last long enough to do that. So here's a little fetch rover, and that's going to go and get these samples. You can see that over here on the right. And then it's going to bring them back to this MAV and load them into the nose of the MAV. The MAV will take off. This rocket is small enough that it could fit inside your kitchen. And that's because Mars has only 38% of the gravity of Earth and not very much atmosphere. And so you can get a rocket into orbit, a very low orbit around Mars with a 7 or 8 foot tall rocket. And so that's what's planned, to get into low Mars orbit, have this little canister with all the samples handed off to another spacecraft that will then return these to Earth. And so it takes 2 more missions, some of them quite complicated, but NASA is really putting in the money, and so is Europe. Europeans are planning to collaborate with us on that. And so that's something else to watch over the next few years, how this all develops. Just kind of in closing, I want to pay a tribute to all the people who have worked in Los Alamos on the Perseverance rover. And so we have 2 plaques that are going to Mars on the instruments that we contributed to. And then there's the whole team that provided the fuel for Perseverance's nuclear power. And that's probably about 50 people, I believe. And so we've had a good time getting to know some of them as well. And so this is a big amount of people, well over 100, several hundred people here in Los Alamos who have worked on this rover. And we're so excited for this rover, as it is just 14 weeks away from landing on Mars. It's over halfway. We actually turned on SuperCam in space this week. So excited that it works, turned it back off, but we're just waiting to use it on Mars. So let's see, I think there is somebody else we're going to introduce here, Nina. Do you want to say anything?
Well, some of you may be familiar with this scene, you'll see, but I think what this says is that ChemCam is actually going to be really useful, not only in the near future, but perhaps a little bit more distant future.
Hey, Johansson. I know you don't like it when I touch the ChemCam, but I'm touching the ChemCam. A lot.
Thanks, Matt Damon. And so the launch was July 30th. We were so sad to not be there, but the landing is going to be February 18. And Bradbury Science Museum, can you have a party for us? Even outdoors? I don't know. Let's see what we can do. I don't know. But even if we don't have a party in person, we can probably have some big virtual event, or certainly NASA is going to, and you can tune into NASA that day. It's going to be about midday or a little bit after midday here in the US. And so just mark your calendar for 4 days after Valentine's Day. It's going to be a great event, and we're so looking forward to it. So with that, this was the last view we had of Percy before it launched. And there it is. The helicopter is actually all buttoned up in the bottom of the rover there. The wheels are all, they're all sterilized and covered. The retro rockets are sitting right here ready to fire to bring this thing down to the ground along with the radar. So there it is, and goodbye, Percy. And we look forward to seeing you on February 18. Thanks, everyone.
All right. Well, we do in fact have a few questions. I mean, my first question is, why not also have a voice chip so you could have a Zoom conference with the rover after it lands as part of your party?
Yeah. In fact, I suggested that this thing needed to not just have a microphone, but it also needed to have a loudspeaker so we could yell at the.
There you go. Okay. So,
pretty bad. The bandwidth on Mars is no good.
Yeah.
Probably not. It doesn't have the kind of network that we're expecting on the moon, I understand. So,
Right.
Not yet. Hopefully, eventually.
yeah. Okay. So let's see. One comment. Excellent science, excellent mission. Congratulations to all, from Galen. And then a number of questions. So one question is, what type of nuclear fuel is used for Perseverance? And does it also have a solar power capability?
I guess I'll take that and just say, so The nuclear fuel is plutonium-238, and that's a non-fission isotope of plutonium. So there is no weapons use for it at all, and it is actually, in the whole scope of things, more safe than other isotopes. And so it was fabricated here, and so just a small amount of that will create 2,400 watt hours per day. That's about 100 watts. Let's see, that's the amount of electricity. And so about it makes 100 watts continuous. And so then we can actually charge up the batteries at night, and then we can run flat out during the day. And it's about 3% efficient. So about 3% of its heat energy gets converted to electricity. And there are no solar panels on this rover. We use the rover deck for a whole lot of other things. And the amount of additional energy we would get from solar panels on this would be really small compared with the amount of energy that we actually get from our nuclear battery. So thanks all of you Los Alamos folks that worked on that.
I'll just throw in a little tidbit here that when I first joined the lab, one of the things that I had a chance to do was go down to the plutonium facility and hold a little ball of Pu-338 that was coated in nickel. And you could definitely feel the heat coming off of it in your hand. So that was kind of cool. And that kind of leads into another question. And there are several, so let me know and I can break it down. But the overall question is, what is the power consumption? And you've talked about that a little bit. General computing resources, communication data rates, and the expected lifetime. And I might say the design time as well, lifetime as well as the expected lifetime.
Tell you what, I'll take the computing and the and the data rate, and then Nina, why don't you talk about the lifetime? So let's see, I don't know if I get all of this, but yeah, I think we answered the power part. So the computing, I'll have to say, I'll let a little secret go here about this rover. It has the same computer as a Curiosity rover, which is a little bit of a downer because that was basically 2004, 2003 vintage computing power. But they wanted, there was a decision very early on to use as much as we could from the old rover. And unfortunately that included the computer. But what they've done is they've added another computer unit on it. So it has parallel processing power, but it's, in the scope of things, it's just a little bit slow, but it's got a lot more memory and parallel processing power. Now, how much data comes down from Mars? We have been getting on average 60 megabytes of data per day, day in and day out, 7 days a week from Mars for the last 8 years. And I think that's actually going up because there are more satellites that are now relaying than there were back in 2012. So that's in one sense a good amount, in another sense not a good amount when you consider that your iPhone, will take a 14 megabyte picture and you only have room for 4 or 5 of those. So we really have to be data careful with what we send back. There's a lot of compression that we use on the images and so on. But that's how it works. And it goes through a relay satellite. So this rover beams the data up to a relay satellite while it's passing overhead. And then that gets beamed back to Earth through the deep space network that NASA has 3 places around the world. And then it goes into the internet. And then we get it from that. So that's the data rate. And I think, let's see, Nina, you were going to talk about the lifetime.
Sure, maybe I'll just jump. I think I saw somebody try to do a calculation. I think it'll take, if you were trying to download 1 episode of Breaking Bad from Mars, it would take you like 13 hours. But that's only if you had all the resources. Yeah. So that's a little slower than maybe we're used to, but I think it's still pretty great. Yeah, so in terms of the lifetime, we have to, put a box around that and say, okay, we're going to last at least this long. But of course, many missions last longer, but it's our goal to last a certain length. So for Perseverance, it has the same lifetime as Curiosity, which would be 1 Mars year, which is actually about 2 Earth years. So that actually sounds pretty short, right? That's what we're aiming for. But of course, Curiosity has definitely blown that out of the water. So now we're, heading into year 9 of Earth years. So divide that in half for Mars. So the chances are high that we'll have a lot more lifetime out of Perseverance than our nominal mission. But of course, we can make no promises. But I have high hopes, especially given seeing how well Perseverance's twin is doing right now on Mars, that we'll have a nice long mission.
Great. Okay, Liv asks, the laser on the SuperCam or KimCam would burn the rocks. Wouldn't that change the chemical substance of the rock?
You want to take that, Nina?
Sure, yeah. Well, that's a great question, right? So what it will do is basically you're vaporizing material, right? So you're not actually destroying it, you're just changing its form. And so when that material cools down, it's going to be the same elements that it was before. Now, of course, you've moved things around a bunch, so maybe that material has changed somewhat. And so sometimes we can actually see that the mineralogy will change from before we analyzed it to after we analyzed it. But all those elements are really going to be still there. So overall, we're still getting the same composition, even though we are kind of messing with the molecules because we're breaking them apart and into their constituent atoms.
Okay. And you have another instrument along with it that helps with some of the mineralization and looking at what those things looked like before it got hit with the laser, the larger laser.
That's right. So the LIBS is going to be the vaporizing laser, but then the Raman is not going to be as powerful, but we can use that to actually look. You could look at a surface before and after the LIBS to be able to see maybe there were some changes. So yeah, we have the capability.
And actually, the Raman looks over a little bit bigger spot than the LIBS, so we don't destroy that whole area.
Okay, interesting. So here's another question from Mitch. How did you size the helicopter rotors and how were they tested?
Well, first of all, this was a JPL project, and it was first of all proposed when we proposed all of the scientific instruments, and it actually didn't win. But the director of Jet Propulsion Laboratory and the heads of NASA liked the idea so much that they decided to turn it into a technology project. And so JPL spent their technology development money. They get a certain amount of money, just like our lab, for some technology development. And so they put that into the helicopter and had a sort of a crack team there that was really working on all of this. But they had to figure out early on how big of a rotor they would have to have, how fast it would go. And it turns out doing a helicopter on Mars is something that we think is barely a capability. The things like getting it warm enough after a Martian night so that its battery can survive, can actually give out the energy to get those rotor blades going is the real key to this. And so that's a real balance for the temperature of this thing. Those rotor blades are about 4 feet in diameter, and this only weighs a little, about 3 pounds, this whole thing. And those rotor blades actually go 8/10 of the speed of sound at the tips of those rotor blades. So it is, like I said, at the limits of capability. So we'll just see what happens when they try to fire that thing up.
Amazing how they can do that with such a thin atmosphere.
Yeah.
Okay, let's see. Go ahead, Nina.
Maybe I'll just throw this out there. So something we're talking about maybe doing is actually trying to listen to what that sounds like with our microphone, because of course it's going to be, making some kind of a racket, but on Mars, with a less dense atmosphere, it's going to be kind of quiet. So hopefully we can actually capture that so you can actually live the moment when we first fire up these rotors.
I wonder if there's any scientific data that one could get from listening to the pitch and breaking down that the waveform of the sound returning from the rotors.
You could learn a lot about the atmosphere. Like any sound traveling through the atmosphere is going to provide you with some really interesting information. And of course, we don't have that information right now. We have some really good ideas about what that is, but it will help us really understand the Martian atmosphere a lot better. So yeah, that is science that we can do.
Okay, Arlene asks, how long could the fuel last? And I'm wondering if that's the plutonium, electrical generation system that you have. If the rover might last a number of years, how long could that last?
So the plutonium itself has a half-life of 88 years, which means that in 88 years, it would have half the energy, half the heat output that it has now. But actually what happens with these is we fabricate the material here, we encapsulate it so that so that nothing can actually breach it or get in. And then we send it off to the Idaho National Engineering Laboratory. And there they made it up with the part that makes the electricity. And it's solid state. There's no moving parts in this, but it's just a hot and a cold junction of metal that actually make the electricity. And but that part has some natural chemical reactions that occur at that junction. And so that limits the lifetime of these. On Curiosity, we know that the power is going down about 3% or 2 or 3% per year. And so Curiosity has been there 8 years. We think it might have another 5 years or so left before it gets to kind of the threshold of when it doesn't really have enough energy to do much of anything. So and Curiosity was delayed 2 years in its launch. So if you sort of kind of add that up together, you might get 15 years possibly on this Perseverance rover. And so, you know, its design life is 2 years, so 2 Earth years. So we really think that it's really more like a decade mission, and that's what I've got in my mind anyway. But we'll see what happens. That's a great question.
Wish my car would last that long. Okay, so Steve Becker mentions that and I remember seeing this as well. He got to see the Pu-238, the plutonium-238 ball before it was coated, and they just turn off the lights for the demonstration and it glows red. So that's kind of cool. Okay, let's see. Let's see, a couple other questions. Oh yes, MOXIE to create the oxygen from the CO2 atmosphere. Are there studies that show that that could actually be scaled up, assuming it works, to the size needed for some kind of an human expedition mission or even a colony mission?
Yeah, so that's a great question too. So this is actually not a brand new technology. This is something that we've been able to do on Earth. So it's something that's well understood. The tricky part, as I said, you know, is like making that work on Mars by itself. It has to really be autonomous because we can't go, you know, let's say we forgot to tighten a screw. Well, that's it. You know, we can't make any modifications. So this instrument has to function somewhat autonomously on Mars, which is a pretty harsh environment. But the answer is about, like, you know, if we can show that this, you know, we can make something that's robust enough to operate on Mars, you know, it would be straightforward to scale that up. And the idea would be that you would want to do this. You would send your future larger MOXIEs to Mars, and then you would make all the oxygen that you would need, plus of course some margin. And you would do this all before you sent astronauts, so that the astronauts would be guaranteed a ride home and also air to breathe before they ever left Earth. And so that's the idea. It would be done over a long period of time in advance.
So it could even be several years in advance.
That's right. It would probably it'd have to be multi-year phases, but it wouldn't be impossible. Certainly, I mean, to me, that makes a lot of sense given how far away Mars is.
Right, right. Okay, so I have to ask this question for those in our audience who saw the Martian movie. When you drop all of those little sample canisters, and they may be there for a few years, what is the likelihood that dust storms could cover the canisters and you wouldn't be able to find them again?
Yeah, that's a good question. So we have a whole, actually a board of people, a group of people who are eminent scientists from MIT and all kinds of places around the US that are actually in charge of trying to help us decide on the samples, decide how to document the composition of the area right around the drill hole, and in fact down the drill hole. And then they are the ones that'll, I'm sure, be helping advise us on where to drop these samples. And in fact, there's even a group of people in Europe that are specially assigned Europeans to help with this too. And so it's an international sort of committee that's really going to be helping us with all of that. There are places where we know that dust might accumulate, and that would be like on the lee side of a dune that we know is moving, and those things happen on Mars. Curiosity has visited some of those, but they're not all over the place. And so much of the places that we visit and go are just bare rock. And we can be pretty darn sure that those things are going to be bare rock for the next millennium. And so that's going to be a good, those will be good places to set these things. There might be a little bit of dust, but it's nothing like a dune or anything that would prevent us from actually getting them. And then the rover's going to take tons of pictures from different, I've seen the document, and it's got to take pictures from at least 2 different angles that'll show exactly where these things are. And so that's how we will know where they are. It's almost, almost like GPS coordinates in a sense. We will have such great imaging documentation. So.
Okay, great. Let's see. I guess the last question is, when you were talking about Sherlock, you mentioned trying to look for organics. What do you mean exactly by organics?
Nina, do you want to take that?
Sure, yeah. So, organics is really just the chemistry that we know builds up life. And so if you, that's things that are based on carbon and hydrogen for the most part, but all those other elements that I was mentioning. So, it's funny because we have this totally different fields of study, like organic chemistry and inorganic, but truly they're really the same thing. We just call one organic because those are the things that life uses to be able to exist. So when we're talking about organics, we're talking about these materials that have carbon, hydrogen, nitrogen, oxygen in them. And they make certain molecules. We know that there are some building block molecules that can be built into larger molecules that can be built into even larger molecules that can be used again by life. And this is only, of course, life as we know it, because we don't have any other examples of life anywhere else. But it's a good place to start. So, I mentioned things like organic carbon. There's a lot of different possible molecules that you could look for. But when we're talking about organics, we're really just talking about, these carbon and hydrogen bearing molecules that can be built up into these larger things. That's sort of a hand wavy thing because that's a whole, of course, field of study. But I hope that answers generally what you're hoping to find.
Okay, great. Thank you. All right. Those are all the questions that came in from the viewers. Nina and Roger, thank you so much again for sharing with us tonight. For those of you who are out there, you may want to join us next week for a special family-friendly Halloween show about black holes, what it could be scarier, by Jonah Miller. Find this event and others on the PEEC website, peeknature.org/events. And thanks again for tuning in. All right. Good night, everyone.
Thanks, everyone.
Thanks. Bye.
Bye.